There is a machine travelling through the dark right now. It left the only world it ever knew nearly half a century ago. It has crossed the orbital paths of every planet in our solar system, flown past 4 alien worlds up close, and then kept going, past the Kuiper Belt, past the termination shock, past the very last whisper of the sun's breath, into a region of space so remote that the signal it sends back home, travelling at the speed of light, takes over 16 hours to arrive. It carries no crew. It has no destination. And soon, for the first time in its long and extraordinary life, it will fall completely silent. This is the story of Voyager 2, the last of its kind, the most widely travelled object humanity has ever built, and the story of where it is going, not just in the next few years, but in the next few thousand and the next few million. It is a story about time in a way that most human stories are not. It is a story about distance in a way that resists easy comprehension. And it is ultimately a story about what it means to send something outward into a universe that does not care, armed only with human ingenuity, human curiosity, and a small golden record of who we are. But to understand where Voyager 2 is going, and what will happen when it finally stops talking to us, we have to begin at the beginning. Part 1. The Alignment of Worlds. In 1964, a young aerospace engineer named Gary Flandreau was sitting in his office at NASA's Jet Propulsion Laboratory in Pasadena, California, working on what seemed at first like a relatively routine orbital mechanics problem. He had been asked to look into possible trajectories for future spacecraft heading toward the outer solar system. What he found changed everything. Flandreau discovered that the planets of the outer solar system, Jupiter, Saturn, Uranus and Neptune, were in the early stages of a rare geometric alignment that would not happen again for approximately 175 years. In celestial mechanics, the configuration of planets at any given moment determines what is and isn't possible for spacecraft navigation. A single probe travelling outward from Earth normally has to carry enormous amounts of fuel to change direction and speed at each planetary encounter. But when the planets are lined up in just the right way, a spacecraft can use the gravitational field of each planet like a slingshot, picking up speed and changing course without burning any propellant at all. This technique is called a gravity assist, and Flandreau's discovery meant that a single spacecraft launched in the late 1970s could, in theory, visit all 4 giant planets of the outer solar system on a single 12-year voyage, instead of the 30-plus years such a journey would otherwise require. The window for this alignment was narrow. It opened in the mid-1970s and would close by the early 1980s. After that, the planets would drift apart, and no similar opportunity would arise until the year 2153. The implication was staggering. This was a once-in-many-lifetimes chance to survey more than half the solar system in a single mission. The opportunity was almost too good to believe. And so NASA, after years of planning, redesign, budget cuts and political battles, began building for it. The original plan was grand in scope, 4 spacecraft visiting 5 planets including Pluto. Costs and priorities trimmed that vision considerably. What eventually emerged was the Voyager program. 2 spacecraft, 2 trajectories, and an ambition that, while smaller than the original dream, still dwarfed almost anything NASA had attempted before. Each Voyager spacecraft would weigh approximately 815 kilograms at launch, about the weight of a large motorcycle, though it resembled nothing so earthly. Each was built around a 10-sided aluminum frame called a decagonal prism. Each carried a 3.7-meter high-gain antenna dish, the dominant feature of its silhouette, which would remain pointed toward Earth throughout the journey to maintain the critical communications link. Extending outward from the main body on long booms were the scientific instruments: magnetometers, cosmic ray detectors, plasma wave sensors, cameras, spectrometers, and a plasma science experiment capable of measuring the speed, density, temperature, and pressure of the charged particle environment the spacecraft flew through. Power was the engineering challenge that would define the mission's entire lifespan, not just its beginning. This far out in the solar system, solar panels kan den dit statsen. Tactics Solamur. Isinas dekins. Arsentans. Patruted chakadated ponds. Instead, each Voyager was equipped with 3 radioisotope thermoelectric generators, or RTGs. These devices work on a beautifully simple principle. Plutonium-238 decays radioactively, releasing heat. That heat is converted directly into electricity through a thermocouple, with no moving parts whatsoever. At launch, each RTG contained 24 pressed plutonium oxide spheres. Collectively, the 3 RTGs provided each spacecraft with approximately 470 watts of electrical power at launch, about what it takes to run 4 or 5 light bulbs. It was not a great deal of power, but it was steady, reliable, and would continue to diminish slowly over decades as the plutonium decayed, losing roughly 4 watts per year. That slow, inexorable decline of power would become the central narrative of Voyager 2's later life. Every decision the mission team would make in the 2020s and 2030s, every instrument switched off, every heater deactivated, every painful choice about what science to sacrifice and what to preserve, flows directly from the physics of radioactive decay that was baked into the spacecraft the day it was built in the mid-1970s. The 2 spacecraft were given different trajectories, which is the source of their different fates and achievements. Voyager 1 was given a faster, more direct path, aimed at giving it optimal encounters with Jupiter and Saturn, particularly Saturn's largest moon, Titan, which was believed at the time to have a thick and scientifically interesting atmosphere. The price of that Titan encounter was steep. It bent Voyager 1's trajectory sharply northward out of the ecliptic plane, the flat disk in which most of the planets orbit, making any further planetary encounters impossible. Voyager 2 was given a different assignment. Its trajectory was designed with flexibility in mind. It would visit Jupiter and Saturn like its twin, but its path was carefully plotted to keep open the option of continuing onward to Uranus and Neptune, a possibility that depended entirely on Voyager 1 successfully completing its Titan flyby first. If Voyager 1 failed at Titan, Voyager 2 could be redirected to compensate. When Voyager 1 succeeded, Voyager 2 was freed to attempt what no spacecraft had ever done, a complete tour of all 4 giant planets of the outer solar system. In terms of the scientific record Voyager 2 would ultimately compile, this distinction matters enormously. To this day, and this point cannot be overstated, Voyager 2 remains the only spacecraft in the history of human spaceflight to have visited Uranus and Neptune. Decades after its flyby of those distant worlds, scientists still rely fundamentally on the data it collected in the 1980s to understand these mysterious ice giants. No return mission has ever been sent. Voyager 2's encounter data remains the primary scientific record. Voyager 2 was the first of the 2 to launch. On August 20th, 1977, it lifted off from Space Launch Complex 41 at Cape Canaveral, Florida, riding a Titan III Centaur rocket into a clear Florida sky. 16 days later, on September 5, 1977, Voyager 1 followed on its faster trajectory. Despite being launched after its twin, Voyager 1 would reach Jupiter first, reach Saturn first, and would ultimately travel further and faster, eventually overtaking all other spacecraft humanity has launched and becoming, as it remains today, the most distant human-made object in the universe. But Voyager 2, the slightly slower, more circumspect sibling, would prove to be the more scientifically prolific of the 2, the one that saw more worlds, collected more unique data, and ultimately crossed the final boundary of our solar system, armed with instruments its twin did not have. Part 2. The Grand Tour Voyager 2 arrived at Jupiter on July 9, 1979, travelling at extraordinary speed, its cameras and instruments drinking in details of the largest planet in the solar system. Jupiter is a world almost too large to comprehend. Large enough to contain more than 1,300 Earths by volume, a churning banded sphere of hydrogen and helium with no solid surface, wrapped in clouds of ammonia and sulfide compounds that tear around the planet at hundreds of kilometers per hour. Voyager 1 had already flown past Jupiter several months earlier, sending back the first close-up images of the planet's swirling atmosphere and stunning revelations about its moons. Voyager 2 arrived to continue and extend that work. The photographs it transmitted back to Earth, a journey that took approximately 52 minutes at the speed of light, were breathtaking. Jupiter's great red spot, a storm system that has been raging continuously for at least 3.5 centuries, was revealed in unprecedented detail as a complex, swirling atmospheric vortex. The planet's cloud bands, which appear as simple coloured stripes from Earth, proved to be intricate structures of rising and falling atmospheric columns, interacting vortices and embedded storms. Voyager discovered a thin, dusty ring around Jupiter, forcing a revision of theories about the origins and mechanics of planetary ring systems. But it was the moons that most transfixed scientists. Jupiter has dozens of moons today, though most are small captured asteroids. Its 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, had been known since Galileo turned his telescope on Jupiter in 1610. But knowing they existed and knowing what they were like are very different things. Voyager 1 had already sent back the first images of Io, revealing active volcanic eruptions. Discovery so startling it fundamentally changed planetary science, because no one had expected to find a geologically active body so far from the Sun's warmth. Voyager 1 found 9 active volcanoes erupting on Io. 4 months later, Voyager 2 found that 8 of the 9 volcanoes were still active. This was not just confirmation of a prior discovery. It was the establishment of a new scientific paradigm, that tidal heating from a large gravitational body like Jupiter could generate enough internal energy to drive volcanic activity on scales never seen on Earth. Europa, the smooth, icy moon, told a subtler story. Its cracked, reddish surface, crisscrossed with dark lines, like an eggshell under stress, hinted at a dynamic subsurface. Voyager discovered that 2 moons in our outer solar system could host oceans on their surfaces, Jupiter's moon Europa and Saturn's moon Enceladus. The spacecraft picked up on the icy surfaces of the 2 moons, and it set the stage for the discovery that these worlds actually have liquid water oceans under their surfaces. Today, Europa is considered one of the most promising candidates for life beyond Earth in our solar system. That entire scientific story, billions of dollars in subsequent research, multiple follow-up missions, decades of theoretical modelling, and profound astrobiological debate, traces its origins to what Voyager 2 and its twin observed in 1979 during those few short hours of close encounter. After Jupiter, Voyager 2 used that planet's massive gravity to slingshot itself onward toward Saturn. The mathematics of this maneuver is worth pausing to appreciate. Jupiter's gravitational field did not just redirect the spacecraft, it added velocity to it, drawing on Jupiter's own orbital energy to accelerate Voyager 2. The planet slowed imperceptibly in its orbit. The spacecraft accelerated enormously. This is not a free lunch. It obeys the laws of conservation of momentum and energy perfectly, but it meant that Voyager 2 could reach Saturn and beyond on far less fuel than any direct trajectory would require. Voyager 2 reached Saturn in August 1981, flying about 14,290 miles closer to Saturn than its predecessor had. Saturn had already been visited by Pioneer 11 and Voyager 1, but Voyager 2's closer pass and different viewing angles added significant new detail to the scientific picture. The rings of Saturn, visible from Earth with a modest telescope and known since Galileo's time, were revealed to be a structure of extraordinary complexity. Voyager 2 provided more detailed images of the ring spokes and kinks, and also the F-ring and its shepherding moons. What had appeared from Earth as a few broad, simple bands resolved into thousands of distinct ringlets, waves and gaps, governed by gravitational resonances with Saturn's many moons. Voyager 2's data suggested that Saturn's A-ring was perhaps only about 300 meters thick, a structure wider than Earth's diameter but thinner in relative proportion than a sheet of paper. When Voyager 2 passed behind Saturn, viewed from Earth, it utilized its radio link to investigate Saturn's upper atmosphere, gathering data on temperature and pressure. In the highest regions of the atmosphere, where the pressure was 70 millibars, Voyager 2 recorded a temperature of 82 Kelvin. minus 191 degrees Celsius. These were not just numbers. They were constraints on physical and chemical models of how Saturn's atmosphere works, how it circulates, how its famous weather systems form and die. The Saturn encounter nearly ended in disaster. After its Saturn flyby, Voyager 2's scan platform experienced an anomaly, causing its azimuth actuator to seize. The scan platform is the mechanism that allows the spacecraft's cameras and instruments to be pointed at targets independently of the orientation of the spacecraft body itself. Without a functioning scan platform, imaging Uranus and Neptune, worlds that were still 4 to 8 years away, would be impossible or severely limited. Engineers at JPL, working across distances that required round-trip communication times measured in hours, carefully diagnosed the problem, devised a workaround, and brought the platform back to limited functionality. The mission would go on. But the incident was a warning. These spacecraft were already beginning to show their age and fragility, and every subsequent step of the journey would require vigilance and ingenuity from the team on the ground. From Saturn, Voyager 2 travelled for 4.5 years toward Uranus. That is not a sentence that conveys the distance involved adequately. Uranus orbits the Sun at an average distance of approximately 19.2 astronomical units, 19.2 times the Earth-Sun distance, or roughly 2.87 billion kilometres. The solar system is large in a way that everyday language struggles to accommodate. The journey from Saturn to Uranus at Voyager 2's speed took roughly the same length of time as a human child takes to grow from birth to starting school. Voyager 2 encountered Uranus on January 24, 1986, returning detailed photos and other data on the planet, its moons, magnetic field, and dark rings. The Uranus flyby was in many ways the most scientifically surprising of Voyager 2's 4 planetary encounters, because Uranus had yielded so little to Earth-based observation. From Earth it appeared as a featureless blue-green disk. Up close it was still not as visually dramatic as Jupiter or Saturn, but the data from Voyager 2's instruments told a story of a deeply strange world. On January 24, 1986, Voyager 2 swept past Uranus at a distance of 81,500 kilometers. The encounter transformed understanding of the planet. Uranus is tilted on its side. Its rotational axis is inclined at roughly 98 degrees to the plane of its orbit, meaning it essentially rolls around the Sun like a bowling ball. The reasons for this extraordinary tilt are still debated, but the leading hypothesis involves a massive collision with a protoplanet-sized body early in the solar system's history that knocked Uranus permanently sideways. 10 new moons were discovered in the Uranus system. The planet's magnetic field was found to be significantly offset from the planet's axis of rotation. That magnetic field offset was deeply puzzling and remains only partially understood today. On Earth, the magnetic field aligns roughly with the rotational axis. On Uranus, the magnetic field is tilted about 59 degrees from the rotational axis, and is also significantly off-center, not originating from the planet's core, but from somewhere in the interior. This is unlike anything seen elsewhere in the solar system, and it fundamentally challenges theories of how planetary magnetic fields are generated. The moon Miranda, the innermost of the 5 large moons, was revealed to be one of the strangest bodies yet seen in the solar system. Detailed images showed huge fault canyons as deep as 20 kilometers terraced layers and a mixture of old and young surfaces. One theory holds that Miranda may be a reaggregation of material from an earlier time when the moon was fractured by a violent impact. Miranda, which is only about 470 kilometers in diameter, barely large enough for gravity to round it into a sphere, displayed a surface that looked as though it had been shattered and reassembled in no particular order, with ancient cratered terrain, abutting smooth young plains, and enormous cliffs that would tower over anything on Earth. It is one of the most geologically bizarre objects in the solar system, and everything we know about it comes from Voyager 2's brief, irreplaceable flyby. The Uranian ring system might be relatively young, and it did not form at the same time that Uranus did. The particles that make up the rings might be the remnants of a moon that was broken up by either a high-velocity impact or torn up by tidal effects. Unlike Saturn's broad, bright rings made of reflective ice, Uranus's rings are narrow and extraordinarily dark, made of material darker than coal. Their origin and composition remain mysteries that only a future mission to Uranus could properly address. In March 2020, NASA astronomers reported the detection of a large atmospheric magnetic bubble, also known as a plasmoid, released into outer space from the planet Uranus, after re-evaluating old data recorded during the flyby. This is a remarkable illustration of how much science remains locked in Voyager 2's 45-year-old data, still yielding discoveries to researchers today who apply modern analytical techniques to measurements made by an aging machine in 1986. And then came Neptune, the final planet, the end of the tour. 30 years ago, on August 25, 1989, NASA's Voyager 2 spacecraft made a close flyby of Neptune, giving humanity its first close-up of our solar system's 8th planet. Neptune is a world approximately 30 times farther from the Sun than Earth, receiving only about 1,000th as much sunlight. It orbits so slowly that a Neptunian year lasts 165 Earth years. When Voyager 2 was launched in 1977, Neptune had not yet completed a full orbit since its discovery in 1846. Wrapped in teal and cobalt-coloured bands of clouds, the planet that Voyager 2 revealed looked like a blue-hued sibling to Jupiter and Saturn, the blue indicating the presence of methane. A massive slate-coloured storm was dubbed the Great Dark Spot, similar to Jupiter's Great Red Spot. But the atmosphere of Neptune presented a profound puzzle that persists to this day. Neptune is extraordinarily dynamic for a world receiving so little solar energy. The planet itself was found to be more active than previously believed, with winds of up to 1,100 kilometers per hour. Subsequent measurements have refined this figure even higher. Voyager 2 measured wind speeds from Neptune's storm to be up to 2,400 kilometers per hour in some regions. On Earth, uneven heat from the Sun tends to spur winds, but on Neptune, heat from the planet itself might be driving these winds. Neptune lacks a surface, so there are no mountains or valleys to slow the wind down. These are the fastest sustained winds in the solar system, and they are generated on a world barely kissed by sunlight. The energy must come from Neptune's interior, but the precise mechanism remains poorly understood. During the Neptune encounter, the spacecraft discovered 6 new moons and 4 new rings. But the single most extraordinary discovery of the Neptune flyby was reserved for its largest moon, Triton. Triton is unlike any large moon in the solar system. It orbits Neptune in the wrong direction. Retrograde, opposite to the direction of Neptune's rotation. This strongly implies it is a captured object, a wanderer from the distant Kuiper belt that strayed too close to Neptune billions of years ago and was gravitationally seized. Instead of a frozen inert body, Triton displayed signs of active cryovolcanism. Voyager 2 captured nitrogen geysers erupting up to 8 kilometers high, reshaping the moon's surface. Its retrograde orbit indicated it was likely a captured Kuiper belt object, evidence of Neptune's violent past. Nitrogen geysers. On a world so cold that its surface is coated with frozen nitrogen and methane ices. On a moon so distant from the sun that it receives only 1,000th of the sunlight that bathes Earth. The solar energy that reaches Triton is enough, just enough, to sublimate a thin layer of frozen nitrogen, creating pressure beneath the ice that vents through weak spots in the surface, erupting in plumes that rise 8 kilometers before being deflected horizontally by the thin atmosphere and depositing dark streaks of material across the icy plains. Triton is not dead. It is alive in ways that challenge every assumption about where activity in the solar system can occur. The conclusion of the Neptune flyby marked the beginning of the Voyager interstellar mission, which continues today. After Neptune, NASA formally redesignated the entire Voyager program. The planetary grand tour was over. A new mission, one that had no predetermined endpoint, no target world, no final destination, had begun. Voyager 2 was now aimed at the interstellar medium, flying southward below the ecliptic plane toward the constellations of Sagittarius and Pavo, heading for regions of space no instrument had ever directly sampled. Part 3. The Long Middle. The years after Neptune were a different kind of science. There were no more planets to visit, no more moons to photograph, no more ring systems to analyze. The cameras had been turned off, not because they had failed, but because there was nothing left to photograph, and because keeping them running consumed power and computational resources that could be better used to keep the fields and particles instruments running. The software that controlled the cameras was deleted from the spacecraft's onboard computers. The computers on the ground that knew how to interpret the camera data were decommissioned. Even if someone wanted to turn those cameras back on today, the infrastructure to do so no longer exists. What remained was a different kind of observation. Voyager 2 was moving through a vast, largely invisible medium, the heliosphere, the Sun's enormous bubble of influence. Understanding this medium required instruments that could not see in the conventional sense, magnetometers that measured the strength and direction of magnetic fields, plasma instruments that measured the properties of charged particles, cosmic ray detectors that counted high-energy particles arriving from interstellar space, and plasma wave sensors that detected electromagnetic fluctuations in the sparse plasma. The heliosphere is the product of the solar wind. The continuous stream of charged particles, mostly protons and electrons, that flows outward from the Sun in all directions at speeds of roughly 400 to 800 kilometers per second under normal conditions. This solar wind fills space out to enormous distances, and it creates a kind of protective bubble around the solar system. Inside that bubble, the Sun's magnetic field dominates. The density and composition of particles is determined by solar activity. The radiation environment is substantially shaped by the Sun. Outside that bubble lies the interstellar medium, the material between the stars, seeded with the remnants of supernovae millions of years old, permeated by a different magnetic field, bombarded by galactic cosmic rays at energies far exceeding those of the solar wind. As Voyager 2 travelled outward through the heliosphere during the 1990s and early 2000s, it was documenting this environment in real time. The data it sent back was steady and scientifically valuable, though less dramatic than the images of alien worlds. It was measuring the gradual weakening of the solar wind with increasing distance, the increasing influence of galactic cosmic rays, the changing character of the magnetic field. It was building a portrait of the outer heliosphere that no other instrument could provide. In 2004, at a distance of approximately 83.7 astronomical units from the Sun, Voyager 2 crossed the termination shock. The termination shock is the first major boundary layer of the heliosphere, the region where the solar wind, rushing outward supersonically, slows abruptly to subsonic speeds because it is encountering the pressure of the interstellar medium. Think of it as the place where the outward push of the solar wind finally begins to feel the pushing back of the rest of the galaxy. At the termination shock, the solar wind dramatically decreases in speed, heats up, and becomes more turbulent. Beyond this boundary lies the heliosheath, a broad chaotic transitional region between the pure solar wind environment inside and the pure interstellar medium outside. In the heliosheath, the solar wind is compressed and heated, magnetic fields pile up, and the two great cosmic environments begin to mix in complex ways that theorists had been trying to model for decades. Voyager 2 spent years traversing the heliosheath, sending back data that tested and in many cases upended those theoretical models. The heliosheath proved to be more structured, more variable, and more surprising than anyone had predicted. It was thicker in some directions than others. It fluctuated with the 11-year solar cycle. It contained unexpected particle populations at unexpected energies. And then, on November 5, 2018, Voyager 2 crossed the heliopause. Part 4. The Crossing. The heliopause is the ultimate outer boundary of the Sun's direct influence, the place where the solar wind pressure finally falls below the pressure of the interstellar medium, and where solar material gives way to material forged in the depths of distant stars. It is not a physical surface, but a dynamic, moving boundary that breathes with the solar cycle, expanding and contracting over years and decades. When Voyager 2 crossed it, the instruments recorded changes so dramatic and sudden that there was no ambiguity about what had happened. The most compelling evidence of Voyager 2's exit from the heliosphere came from its onboard plasma science experiment, an instrument that had stopped working on Voyager 1 in 1980, long before that probe crossed the heliopause. This is the crucial difference between the two spacecraft's heliopause crossings. When Voyager 1 crossed the heliopause in 2012, its plasma instrument was already dead, having failed 32 years earlier. Scientists could infer the crossing from other instruments, but they could not directly measure the properties of the plasma at and beyond the boundary. Voyager 2 carried a working instrument that would provide first-of-its-kind observations of the nature of this gateway into interstellar space. The PLS uses the electrical current of the plasma to detect the speed, density, temperature, pressure, and flux of the solar wind. The PLS aboard Voyager 2 observed a steep decline in the speed of the solar wind particles on November 5th. Since that date, the plasma instrument had observed no solar wind flow in the environment around Voyager 2, which made mission scientists confident the probe had left the heliosphere. The crossing was swift. The heliopause transition occurred in less than 1 day. 1 day, and an object launched from Earth had transitioned from the Sun's domain to the interstellar medium, from one cosmic environment to another, from inside to outside. On November 5, 2018, Voyager 2 observed a sharp decrease in the intensity of low-energy ions and a simultaneous increase in the intensity of cosmic rays, indicating that Voyager 2 had crossed the heliopause at 119 astronomical units and entered interstellar space. 5 research papers published simultaneously in the journal Nature Astronomy in November 2019 detailed what the 5 operating instruments of Voyager 2 had observed at and beyond the crossing. Each paper told part of the story from a different scientific perspective, and together they painted a picture more complex and nuanced than any single description can convey. The plasma inside the heliosphere is hot and sparse, while the plasma in interstellar space is colder and denser. Those 4 words, hot and sparse versus cold and dense, represent a fundamental distinction between 2 great cosmic environments, a distinction that Voyager 2 confirmed by direct measurement for the first time. The first electron density, measured by the Voyager 2 plasma wave instrument in the interstellar medium, was 0.0039 electrons per cubic centimetre on January 30, 2019, at a heliocentric radial distance of 119.7 astronomical units. The density jump, about a factor of 20, confirmed that Voyager 2 had crossed the heliopause, 20 times denser. Crossing the heliopause is like moving from a near vacuum into something that, while still extraordinarily sparse by terrestrial standards, is 20 times more populated with matter. A plasma boundary region with a width of 1.5 astronomical units was observed before the heliopause. The plasma in this boundary region slowed, heated up, and was twice as dense as typical heliosheath plasma. A much thinner boundary layer began about 0.06 astronomical units inside the heliopause, where the radial speed decreased and the density and magnetic field increased. An observation by Voyager 2's magnetic field instrument confirmed a surprising result from Voyager 1. The magnetic field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere. Before these measurements, scientists had debated whether the interstellar magnetic field would align with or cut across the heliosphere's own magnetic field. The answer, that they run roughly parallel, was something no theoretical model had clearly predicted. With Voyager 1, scientists had only one sample of these magnetic fields, and couldn't say for sure whether the apparent alignment was characteristic of the entire exterior region, or just a coincidence. Voyager 2's magnetometer observations confirmed the Voyager 1 finding and indicated that the two fields align. The Voyager probes are showing us how our Sun interacts with the stuff that fills most of the space between stars in the Milky Way galaxy. Without this new data from Voyager 2, we wouldn't know if what we were seeing with Voyager 1 was characteristic of the entire heliosphere or specific just to the location and time when it crossed. These words from Ed Stone, the Voyager project scientist who has held that role since 1975, capture the essential value of having two spacecraft cross the heliopause in different locations, in different directions, at different times in the solar cycle. The scientists learned through Voyager 1 and Voyager 2 data of their crossings that particles of solar wind and of the interstellar space wind actually spill across the boundary. The wind from interstellar space is created by stars that went supernova millions of years ago. The mix-in of these particles actually creates a layer between the heliopause and interstellar space. Think about what that means. The particles that Voyager 2 detected just outside the heliopause are the ancient remnants of stellar explosions. Stars that burned and died millions of years before the Earth formed in different parts of the galaxy, flung their material outward at enormous velocities, and some of that material has drifted across interstellar space to accumulate in the local medium surrounding our solar system. Voyager 2 is sailing through the residue of ancient catastrophes, measuring it directly, sending those measurements back to a pale blue dot orbiting a relatively unremarkable star on the edge of a spiral arm. The big surprise was that the two probes encountered the heliopause at about the same distance from the Sun, even though one occurred at high solar activity and the other one at low activity. We don't understand why that is. The Sun's activity cycle, which runs roughly 11 years from solar minimum to solar maximum and back, was expected to drive significant variations in the heliopause distance. A more active Sun pushes out more solar wind, expanding the heliosphere. A quieter Sun allows the heliosphere to contract. Voyager 1 and Voyager 2 crossed the heliopause about 6 years apart, at different points in the solar cycle, and yet at nearly the same distance. 121.7 AU for Voyager 1 and 119 AU for Voyager 2, just 2. 7 AU apart. This near symmetry was not predicted and remains unexplained. The new papers confirm that Voyager 2 is not yet in undisturbed interstellar space. Like its twin Voyager 1, Voyager 2 appears to be in a perturbed transitional region just beyond the heliosphere. The interstellar medium, immediately outside the heliopause, is not the pristine, undisturbed material of the distant galaxy. It is a region still influenced by the heliosphere's presence, disturbed by shock waves from solar activity that penetrate the heliopause and propagate outward, and affected by the complex dynamics of the heliosphere-ISM interface. Truly undisturbed interstellar space, if such a thing exists on these scales, lies considerably further out. The interstellar medium in the vicinity of the Sun belongs to what astronomers call the local interstellar cloud, a diffuse region of partially ionized gas that our solar system has been moving through for roughly the last 60,000 to 150,000 years. The local interstellar cloud is itself embedded within a larger structure called the local bubble, a vast, roughly ellipsoidal cavity in the interstellar medium approximately 300 light-years across, blown out by a series of supernova explosions over the past 10 to 20 million years. The walls of the local bubble are dense with molecular gas and star-forming regions. The interior, where we live, is comparatively empty, hot and tenuous. Voyager 2 is currently sailing through the inner regions of this local bubble, measuring its properties directly. No other spacecraft will do so for decades, if ever. Part 5. The dying of the light. The radioisotope thermoelectric generator on each spacecraft puts out 4 watts less each year, 4 watts per year. That doesn't sound like much. But over nearly 5 decades of operation, the accumulated loss is devastating. The 470 watts that Voyager 2 had at launch has declined to approximately 240 watts today, barely half of what it started with. And the instruments, heaters, computers, transmitters and attitude control systems that keep the spacecraft alive and talking all draw on that diminishing pool of energy. For decades, the power management strategy was relatively straightforward. Turn off instruments no longer needed for the current phase of the mission. Deactivate heaters for systems that were deemed acceptable to let cool, and carefully prioritize the remaining power among the remaining functions. The cameras went off shortly after Neptune. Various subsystems were deactivated through the 1990s. Through the 2000s and 2010s, the science instruments themselves began to be shut down one by one. But in 2023, the JPL engineering team faced a starker choice than any previous conservation measure. The natural options had been exhausted. The next thing on the list was not a redundant backup system or a long-dormant instrument. It was the science itself. In search of a way to avoid shutting down a Voyager 2 science instrument, the team took a closer look at a safety mechanism designed to protect the instruments in case the spacecraft's voltage changes significantly. Because a fluctuation in voltage could damage the instruments, Voyager is equipped with a voltage regulator that triggers a backup circuit in such an event. The circuit can access a small amount of power from the RTG that is set aside for this purpose. Instead of reserving that power, the mission would now use it to keep the science instruments operating. This was a calculated risk. The safety net was being removed to keep the science running. But the engineering team judged the risk acceptable. After more than 45 years in flight, the electrical systems on Voyager 2 had proven remarkably stable. The probability of a voltage fluctuation severe enough to damage the instruments was low, and the value of the data being collected was high. That workaround bought more time, but time, like power, was finite. In October 2024, NASA operators turned off Voyager 2's plasma science experiment. The plasma science experiment had been one of the most important instruments on the spacecraft. The very instrument that had provided the definitive direct measurement of the heliopause crossing in 2018 that Voyager 1's defunct plasma instrument could not. It had been collecting limited data in the years before its shutdown due to the orientation of Voyager 2 in relation to the flow of plasma beyond the solar system. It was, by the standards of a spacecraft running on fumes, a defensible loss. But it was a loss. On March 24, 2025, NASA shut off Voyager 2's low-energy charge particle instrument, leaving it with only 3 active instruments: the triaxial fluxgate magnetometer, the cosmic ray subsystem, and the plasma wave subsystem. 3 instruments. 3 windows onto the interstellar universe. 3 remaining reasons for the Deep Space Network to maintain its decades-long vigil over a machine more than 20 billion kilometers away. Voyager 2 will continue to operate its magnetic field and plasma wave instruments for the foreseeable future. Its cosmic ray subsystem is scheduled to be shut off in 2026. With the implementation of this power conservation plan, engineers believe the 2 probes could have enough electricity to continue operating with at least 1 science instrument into the 2030s. Into the 2030s. Not indefinitely, not forever. Into the 2030s. Suzanne Dodd, Voyager project manager at JPL, said, "The Voyagers have been deep space rock stars since launch, and we want to keep it that way as long as possible. But electrical power is running low. If we don't turn off an instrument on each Voyager now, they would probably have only a few more months of power before we would need to declare end of mission." End of mission. Those 3 words, spoken matter-of-factly by a program manager discussing engineering trade-offs, carry an enormous weight when you stop to consider what they mean. End of mission does not mean the spacecraft stops moving. Voyager 2 will continue on its current trajectory essentially forever. The laws of physics do not allow it to simply stop. It will keep travelling at approximately 55,000 kilometers per hour relative to the Sun, covering roughly 1.5 billion kilometers every year for the rest of time. End of mission means something more specific, and in some ways more poignant. End of communication. The moment when the last instrument falls silent. The moment when the Deep Space Network receives the last signal. The moment when Voyager 2 becomes, for all practical purposes, invisible to us. An artifact, an ambassador, a message in a bottle sealed and thrown into an ocean so vast that any hope of recovery is not just improbable, but cosmologically impossible. The Deep Space Network that communicates with Voyager 2 is itself an extraordinary technological achievement that deserves a moment's attention. Communications are the responsibility of Australia's DSS-43 communication antenna near Canberra. The Canberra antenna is the primary Earth station for Voyager 2 because of its position in the southern hemisphere. Voyager 2 is currently flying below the ecliptic plane, heading south in the sky, and can only be communicated with via antennas in the southern sky. This geographic constraint is not academic. In early 2020, DSS-43 had to be taken offline for critical upgrades and maintenance. For approximately 8 months, NASA could not communicate with Voyager 2 at all. They could send signals, but could not be confident of a response. The probe was instructed to maintain autonomous operation and not to make any autonomous changes that might compromise the mission. It complied. When DSS-43 came back online, Voyager 2 was still there, still operational, still sending data. As of September 2023, Voyager 2 is transmitting scientific data at about 160 bits per second. 160 bits per second. Your home internet connection likely handles hundreds of millions of bits per second. The most sophisticated scientific data ever collected from the edge of the solar system arrives at Earth's great antennas at a rate equivalent to a few characters of text every second. The transmission power of Voyager 2's radio transmitter is approximately 22 watts, slightly less than a kitchen refrigerator light bulb. That 22-watt signal has to travel more than 20 billion kilometers and arrive at Earth's antennas as a whisper of electromagnetic energy far too faint for any ordinary receiver to detect, requiring the enormous dish antennas of the Deep Space Network and extraordinarily sensitive receivers to extract coherent data from the noise. The fact that this works at all is remarkable. The fact that it has been working with increasingly sparse resources on the spacecraft end for nearly 50 years is one of the genuine engineering marvels of human civilization. But it cannot work forever. The 2 Voyager spacecraft could remain in the range of the Deep Space Network through about 2036, depending on how much power the spacecraft still have to transmit a signal back to Earth. 2036 is not a firm deadline. It is a projection, a best estimate based on current power decline rates and current instrument configurations. The actual end could come a few years earlier or later, depending on whether the spacecraft encounter unexpected technical problems, whether the creative engineering solutions that have extended the mission thus far continue to yield results, and whether the power curve holds to its expected trajectory. What is certain is that the end is close in human terms. Not in astronomical terms. In astronomical terms, what happens in the next decade is a rounding error. But on the human scale, the scale of living memory and working careers and funded programs, the silence is near. When it comes, the last signal from Voyager 2 will arrive at Earth's antennas after more than 16 hours of travel at the speed of light. Engineers will notice the carrier signal fading, not disappearing in a single dramatic moment, but declining gradually, slipping below the noise floor, becoming indistinguishable from the cosmic background. They will attempt to re-establish contact. They will try different frequencies, different command sequences, different antenna configurations. Some of these attempts may temporarily revive a detectable signal, but eventually, hours or days or weeks later, the last intelligible bit will have arrived, and Voyager 2 will go silent. Nothing lasts forever, not even plutonium. Part 6. The Golden Record. Before we follow Voyager 2 further into its silent future, there is one object aboard the spacecraft that demands its own contemplation, because it is unlike anything else humanity has ever created for any purpose. The Voyager Golden Record. The idea originated with Carl Sagan, the astronomer and science communicator whose vision of the cosmos as a vast arena for the possible existence of other intelligence drove some of the most creative thinking in 20th century science. When it became clear in the mid-1970s that the Voyager spacecraft would escape the solar system entirely, would leave our sun's gravitational influence and travel through interstellar space, Sagan and a small committee of scientists, artists and humanists saw an extraordinary opportunity. These spacecraft would become, in a very real sense, the first human-made objects to travel to another star system. Not soon, not in any time scale that a human could conceive of as soon, but eventually, certainly, inexorably. What should we say to whoever or whatever might find them? The committee created the Voyager Golden Record, a 12-inch gold-plated copper disc containing 116 images, a selection of natural sounds from Earth. 90 minutes of music from multiple cultures and traditions, and spoken greetings in 55 human languages, plus a printed message in the language of science, mathematics and physics, that any technologically advanced civilization might conceivably decode. Both Voyager space probes carry a gold-plated audiovisual disc, a compilation meant to showcase the diversity of life and culture on Earth in the event that either spacecraft is ever found by any extraterrestrial discoverer. The record is protected on one face by the spacecraft body, minimizing its exposure to the interstellar environment. The other face is exposed to the cosmos. Scientists who have studied the long-term fate of the Golden Records have concluded that depending on the trajectory the spacecraft takes over the coming millions of years, the record could remain physically intact and potentially legible for an extraordinarily long time, billions of years in the most optimistic scenarios. The information encoded on it is not a snapshot of a civilization at its peak. It is, by its very nature, a snapshot of a civilization at a particular moment. 1977, in the midst of the Cold War, sending two small machines toward the edge of the known universe, wondering whether anyone would ever find them. The music on the record includes Bach, Beethoven, Stravinsky and Chuck Berry. It includes Azerbaijani bagpipe music, Peruvian panpipes, and the gamelan of Java. It includes a 3,000-year-old piece of Chinese music and a dark blues song from the Mississippi Delta. The spoken greetings span dozens of languages, many of which might be extinct or dramatically transformed within a few thousand years. The sounds of Earth include rain, surf, wind, thunder, crickets, frogs, and whales. The images include diagrams of human anatomy, photographs of coastlines and forests, pictures of a family eating dinner and a child being born. It is, by any measure, a profoundly incomplete and imperfect representation of humanity. Carl Sagan himself knew this better than anyone. But completeness was never the goal. The goal was presence. A gesture toward the universe that says, here we were at this moment, on this world, reaching outward. That gesture is now travelling at 55,000 kilometers per hour through the interstellar medium, carrying with it the record of a civilization that built it and may not survive long enough to know if anyone ever hears the music. Part 7. Where the silence will find it, let us follow Voyager 2 into its future now. Not the human-scale future of the next decade, but the deep future of the next few centuries, the next few thousand years, the next few million years. The science of orbital mechanics allows these projections to be made with reasonable confidence over the shorter timescales and with increasing uncertainty over longer ones. What follows is, as best as modern astronomy can determine, where Voyager 2 is going. At the moment of its final silence, sometime in the early to mid-2030s most likely, Voyager 2 will be roughly 155 to 165 astronomical units from the Sun, depending on exactly when that silence falls. It will be travelling at approximately 15 kilometers per second relative to the Sun, heading southward below the ecliptic plane toward the constellations of Sagittarius and Pavo in the southern sky. Its heading places it on a trajectory that takes it away from the Sun at roughly 3.1 astronomical units per year, 465 million kilometers annually, 1.27 million kilometers per day. It will be alone, completely, utterly, cosmically alone. The nearest object of any significance, another spacecraft, another planet, the nearest star, will be light-years away. The Sun, which will still be the brightest star in the sky for thousands of years, will shrink to a point of light indistinguishable to the naked eye from any other bright star, though recognizable to a sophisticated instrument by its position in the sky. Earth will be invisible, lost in the Sun's glare. The solar system will have contracted, from Voyager 2's perspective, to a single bright star in a field of billions. It will take about 300 years for Voyager 2 to reach the inner edge of the Oort cloud, and possibly about 30,000 years to fly beyond it. The Oort cloud is one of the least understood large-scale structures in astronomy because it is effectively invisible to our instruments. We know it exists primarily because of the comets it sends inward. Long-period comets with orbital periods of thousands to millions of years, which could only originate in a reservoir of icy bodies at the extreme outer edges of the solar system's gravitational influence. The inner edge of the main part of the Oort cloud could be as close as 1,000 astronomical units from the Sun. The outer edge is estimated to be around 100,000 AU. Voyager 2 will enter this region roughly 3 centuries from now. The objects within the Oort cloud are sparse, far more widely separated than the asteroids of the main belt, or even the objects of the Kuiper belt. Voyager 2 is statistically very unlikely to actually hit anything. The cloud is better described as a vast population of potential trajectory-altering gravitational influences than as a navigational hazard. Voyager 2 will drift through this region for the better part of 30 millennia, essentially invisible to any astronomer on Earth. After roughly 300 years inside the Oort cloud's inner region, and several thousand more years traversing its outer reaches, Voyager 2 will begin to feel something new, the gravitational pull of other stars becoming comparable to, and then exceeding, the gravitational pull of the Sun. This is the true edge of the solar system. Not the heliopause, not the Kuiper belt, not even the inner Oort cloud, but the gravitational boundary where our Sun loses its claim on the objects that orbit it, and the stars of the galaxy take over. Not until about 20,000 years from now will the Voyagers pass through the Oort cloud and finally wave goodbye to the solar system of origin. At that point, for the first time, the craft will begin to feel the gravitational pull of other stars more strongly than that of the Sun. 20,000 years from now, when Voyager 2 was launched, human civilization had been building cities for roughly 10,000 years. Written language had existed for about 5,000 years. In 20,000 years, our civilization has no way of knowing what form it will take, whether it will still exist, or what the night sky will look like to whoever looks up from Earth's surface. The continents will have shifted slightly. The Earth's axis will have wobbled through another half-precession cycle, changing which stars appear at the poles. The Sun will be almost imperceptibly older, and Voyager 2, still moving at the same relentless 15 kilometers per second, will be clearing its final farewell to its home system. About 61,000 years from now, Voyager 2 will pass beyond the Oort cloud entirely. 61,000 years. To put this in human terms, Homo sapiens may be only about 300,000 years old as a species. The cave paintings at Lascaux are roughly 17,000 years old. The agricultural revolution began approximately 10,000 years ago. At 61,000 years from now, Voyager 2 will clear the last traces of the Sun's family and enter what can unambiguously be called interstellar space for the first time. Not just beyond the heliopause, not just beyond the solar wind, but beyond the gravitational family of our star entirely. And then comes the nearest stellar encounter. In about 40,000 years, Voyager 2 will come within about 1.7 light-years of a star called Ross 248, a small star in the constellation of Andromeda. Ross 248 is a red dwarf star currently located approximately 10.3 light-years from the Sun. It is a small, cool, dim star, far less luminous than the Sun, with a surface temperature of roughly 2,700 Kelvin compared to the Sun's 5,778 Kelvin, and a mass of about 17% of the Sun's. It is unremarkable in almost every way. It has no known planets, though the absence of a detection is not the same as the absence of planets. To any intelligence living in the vicinity of Ross 248 tens of thousands of years from now, if any such intelligence exists, which is entirely speculative, Voyager 2 will pass at a distance of 1.7 light-years. This is far outside the habitable zone of Ross 248, far outside any plausible planetary system, roughly comparable to the outer Oort cloud distance from the Sun, if Ross 248 has one. Any inhabitants of the Ross 248 system who detected Voyager 2 would need extraordinarily sensitive instruments to do so. But 1.7 light-years is, on the cosmic scale, close. The current nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. During Voyager 2's encounter with Ross 248, it will be closer to that star than we are to Proxima Centauri today. It will be, briefly, a traveller from a foreign solar system passing near someone else's neighbourhood. At that point, Ross 248 will also briefly be the closest star to our Sun, at a distance of only 3.02 light-years, as its own proper motion through the galaxy carries it into our stellar neighbourhood temporarily before it drifts away again. If undisturbed for 296,000 years, Voyager 2 should pass by the star Sirius at a distance of 4.3 light-years. Sirius is the brightest star in Earth's night sky, a brilliant blue-white star approximately twice as massive as the Sun. In 296,000 years, it will be a distant backdrop as Voyager 2 sails past at nearly 10 times today's Earth-Sun distance from the nearest bright star in our sky. But none of these stellar encounters are destinations. Voyager 2 is not bound for any of them. It is not aimed at anything. It is simply moving in the direction that the forces acting on it 47 years ago sent it, and will continue moving in approximately that direction, perturbed by stellar gravity, by dust clouds, possibly by the gravity of rogue planets wandering through the interstellar medium, essentially forever. Beyond the outer edge of the Oort cloud, the gravity of other stars begins to dominate that of the Sun. Both spacecraft will continue on their journeys outward, passing through scattered dust clouds on their way through the local bubble, a cavern of relatively empty space blown by tempestuous dying stars. They will exit this bubble in 5.7 million years. 5.5 million years from now, Voyager 2 will breach the wall of the local bubble and enter the denser interstellar medium of the Milky Way proper. The dust and gas concentrations it will encounter, there are orders of magnitude higher than the near vacuum of the local bubble. Whether the physical structure of the spacecraft, already 500 million years old by this point, survives the transition intact is uncertain. The slow erosion of micrometeorite impacts, the sputtering of interstellar ions on metallic surfaces, and the ultraviolet and X-ray radiation of the galactic environment will have been degrading the spacecraft for millions of years by this point. The aluminum, titanium and copper structures may remain identifiable as artificial objects, but the more delicate components, electronics, cables, the gold plating of the record, will be in various states of degradation, depending on exactly what environments the spacecraft passes through. The main reason that Voyager 2's trajectory is more uncertain over the long term is that the orbit it is flung into is more chaotic, and it is significantly more difficult to predict with any certainty exactly what sort of environment it will be flying through. There may be a whole population of rogue planets out in interstellar space. A mildly close encounter with one of those could change the itinerary significantly. Rogue planets, worlds that formed around stars and were subsequently ejected by gravitational interactions, or that formed in isolation in the interstellar medium, may be surprisingly common. Some estimates suggest there may be more rogue planets in the galaxy than stars. If Voyager 2 makes even a distant encounter with one, the gravitational perturbation could redirect its trajectory significantly, setting it on a path very different from anything current projections can predict. On timescales of hundreds of millions to billions of years, the trajectory of Voyager 2 becomes essentially unpredictable. The galaxy itself will change. In approximately 4.5 billion years, the Milky Way and the Andromeda Galaxy are expected to begin their collision and eventual merger, an event that will take hundreds of millions of years to complete and will fundamentally reorganize the stellar populations of both galaxies. Where Voyager 2 is at that point, and what gravitational influences it has encountered along the way, is impossible to say. What can be said is this: Voyager 2 will not stop. There is no friction in interstellar space to slow it. There is no wall to hit. There is no attractor powerful enough to pull it back. It will continue, diminished and silent and alone, for as long as the universe endures, which, by current cosmological understanding, means for trillions upon trillions of years. Long after the Sun has exhausted its hydrogen fuel and swelled into a red giant, long after the Earth has been consumed or rendered lifeless, long after the last red dwarf star has cooled to a dark cinder, Voyager 2 will still be moving through whatever the universe has become. Part 8. What the last signal means. There is a question that hovers over this entire story, and it deserves direct attention. Why does it matter? Why should anyone care what happens to a 815-kilogram machine built nearly 50 years ago with computing power inferior to a modern wristwatch, now sailing silently through the interstellar dark? The answer, or one version of it, begins with what Voyager 2 has actually done, the concrete, verifiable scientific contributions that changed our understanding of the solar system and the universe. It gave us Jupiter as a world of active geology, with volcanically active moons and a ring system we didn't know existed. It gave us Saturn's rings in detail no telescope could match. It gave us Uranus as a tilted, magnetically bizarre ice giant with moons that shatter every assumption about what small bodies in the outer solar system are supposed to look like. It gave us Neptune as a world of violent weather and captured moons that erupt nitrogen geysers in the cold dark far from the sun. It gave us the first and so far only direct measurements of the heliopause from a spacecraft with a functioning plasma instrument, establishing fundamental properties of the boundary between our Sun's domain and the interstellar medium. It gave us 2 data points. In 2 different directions, at 2 different times in the solar cycle, for the structure of the very local interstellar medium, data that cannot be replicated by any Earth-based or Earth-orbiting observatory. These are not trivial contributions. They are the foundation of entire scientific subdisciplines. The study of icy moons as potential habitable environments, which drives mission planning for Europa Clipper, for future Enceladus landers, for the proposed Uranus orbiter. Traces its intellectual lineage directly to what Voyager 2 found. The science of heliophysics, the study of the Sun's sphere of influence and its interaction with the interstellar environment, was transformed by Voyager's crossings. The physics of magnetospheres, the dynamics of planetary ring systems, the geology of small bodies in the outer solar system. Voyager 2 touched all of these fields and changed them. But there is something else, something harder to quantify, but no less real. The Voyager spacecraft represent a particular kind of human achievement. not the achievement of a single genius or a single nation or a single decade, but the sustained achievement of hundreds of people working across many decades, adapting to unexpected challenges, finding creative solutions to problems no one had anticipated, and choosing consistently to keep the mission going, even when it would have been easier to let it end. The engineers who wrote software patches to work around a failing memory chip on Voyager 1 in 2023, doing so across a 45-hour round-trip communication delay, were doing something genuinely extraordinary. The team that found a way to tap the emergency power reserve to keep Voyager 2's instruments running a few years longer was not following a manual written in 1977. They were improvising, innovating, reaching for solutions in real time, driven by the same impulse that launched these spacecraft in the first place, a refusal to accept that we cannot know more. And then there is the golden record, the message in the bottle, the gesture toward the unknown. Whatever one thinks about the probability of extraterrestrial intelligence, and reasonable scientists hold widely varying views on this question, the act of placing that record on those spacecraft was not primarily an act of communication. It was an act of meaning-making. It was a civilization deciding consciously and deliberately that its first emissaries to the stars would carry not weapons, not territorial claims, not distress signals, but music. Art, science, greetings, the sound of rain on leaves, the call of a humpback whale, Bach, Chuck Berry, a child's first cry. That decision tells us something about ourselves, something that transcends the particular politics, conflicts and failures of 1977 or any other year. It tells us that when forced to distill ourselves to our essence, to choose what to say to the universe about who we are, we chose wonder. We chose beauty. We chose connection, even across distances so vast that no reply is possible within any human time frame. Part 9. The Last Place. So what is the last place Voyager 2 will ever reach before it dies? The question can be answered on multiple levels depending on what we mean by reach and what we mean by dies. If we mean the last scientifically meaningful destination, the last place where Voyager 2 will exist as a functioning scientific instrument sending data back to Earth, that place is approximately 155 to 165 astronomical units from the Sun, somewhere in the very local interstellar medium, probably in the mid-2030s. Engineers believe the two probes could have enough electricity to continue operating with at least one science instrument into the 2030s. At that final moment of transmission, Voyager 2 will be roughly 23 billion kilometers from the point on Earth where the last signal arrives at a deep space network antenna. It will be deeper in interstellar space than any human-made object has ever been when it stopped communicating. Its signal will carry measurements of the interstellar magnetic field, or plasma wave data, or cosmic ray fluxes, depending on which instrument is the last to fall silent. And that last data point, that final measurement of some property of the interstellar medium from a distance never before sampled, will be science. Real science, irreplaceable science, knowledge that cannot be obtained any other way. The last place Voyager 2 reaches as a scientific instrument is a place of genuine discovery, a location in the very local interstellar medium that was unknown and unknowable until a 47-year-old spacecraft, running on the residual decay of a handful of plutonium spheres, reached it. If we mean the last place Voyager 2 will ever physically reach, the ultimate destination, the final location, the answer is more poetic and more honest. There is no such place. The last place Voyager 2 will ever reach is everywhere it hasn't been yet, which is the overwhelming majority of the universe. It will never stop arriving. It will never find the boundary. It will pass through the walls of the local bubble in 5 million years and into the denser galaxy beyond. It will drift through the stellar nurseries and cloud complexes of the Milky Way's spiral arms over hundreds of millions of years. It will survive the Andromeda collision. It will wander through whatever the galaxy becomes in its aftermath. On timescales of billions of years, the Sun will die, the Earth will be gone, and everything that made Voyager 2's launch possible will have ceased to exist. But Voyager 2 itself, or the ghost of it, whatever physical coherence remains, is still moving the atoms that constitute it were forged in stellar nucleosynthesis billions of years ago. There will still be those atoms when they are dispersed by whatever forces eventually dismantle the spacecraft. A collision with a dust cloud, a close encounter with a stellar remnant, the slow erosion of micrometeorites over geological time. Those atoms will return to the interstellar medium from which they came, enriched by the brief, improbable adventure of being assembled into a spacecraft by a short-lived species on a small planet orbiting an ordinary star. This is, in the end, what the last place Voyager 2 will ever reach tells us about everything. We live on a world that is fragile and temporary. Our sun will burn for another 5 billion years, but its eventual death is as certain as anything in physics. The thin envelope of breathable atmosphere, the liquid water, the moderate temperatures that allow complex chemistry, all of it is contingent, all of it is bounded by time. We are not eternal. We will not be here in 5 billion years, or perhaps even in 500. But we launched Voyager 2, and we gave it a record of who we are. And it will carry that record through the death of our sun, through the dispersal of our solar system's material back into the interstellar medium, through the long dark decline of stellar activity as the universe ages and cools, potentially for billions of years. It is the most durable thing we have ever made, not because of the engineering, though the engineering is extraordinary, but because of what it represents, our desire to be known, our insistence on reaching outward, our refusal to accept that the universe ends at the edge of what we can see. Sometime in the next 10 to 15 years, a team of engineers at JPL will be sitting in front of their consoles, watching a signal degrade. The carrier tone from Voyager 2, which they have been tracking for decades, will be getting weaker. The last instrument will be drawing its last few watts of power from the slowly dying RTGs. The data will be increasingly noisy, decreasingly reliable, increasingly punctuated by the static of deep space. They will have known this day was coming for a long time. Some of them will have worked on the Voyager mission for most of their professional lives. Some will be new to the team, hired specifically to manage the mission's final years. All of them will know that what they are watching is not just the end of a spacecraft's operational life, but the end of something that began nearly half a century ago, when a Titan rocket rose from Cape Canaveral and a 815-kilogram machine began the most ambitious journey in human history. The signal will fade. It will drop below the noise floor. The computers will flag it. Someone will announce it. There may be silence in the control room, or there may not. These are professional scientists and engineers. They will have prepared themselves for this moment. But prepared and not affected are different things. And then Voyager 2 will continue on its way, as it always has, indifferent to the silence it has left behind. It will cross another astronomical unit of interstellar space. Then another. Then another. Year by year, decade by decade, century by century, it will move further from the last moment anyone heard its voice. The Oort cloud waits, 3 centuries ahead. Beyond that, the gravitational edge of the solar system, 20,000 years out. Beyond that, the closest stellar flyby, 40,000 years away. Beyond that, everything else. The galaxy, the cluster, the supercluster, the universe, opening ahead of it in all its inconceivable vastness. It was a wonderful journey that began with the launch of 2 spacecraft in 1977 to explore Jupiter and Saturn. And it will not end. Not really, not ever. The last place Voyager 2 will ever reach before it dies is not a place at all. It is a moment, the moment when the last signal arrives and the universe becomes a little bigger and a little quieter and a little more full of the ghost of our reaching. We built it. We launched it. We listened to it for nearly 50 years. We learned from everything it told us. And then, in the early decades of the 21st century, it fell silent in the night, still moving, still carrying our message, still hurtling through the interstellar dark on a journey that will not end until the stars themselves go out. That is what it means to explore, not to arrive, not to conquer, not to claim, but to reach and keep reaching, even after the reaching can no longer be heard. Voyager 2 is out there right now, tonight, in the interstellar dark, approximately 21 billion kilometers from the point on Earth where you are reading these words. Its last instrument is ticking, measuring some property of the space between the stars. Its RTGs are still warm, barely, glowing with the residual heat of decaying plutonium. Its 3.7-meter antenna is still pointed at Earth. Not because it knows where Earth is, but because the engineers who built it 47 years ago calculated where Earth would be, and programmed the attitude control system to keep it pointing there, and the thruster fuel to maintain that pointing is not yet exhausted. It is still talking to us. And in the small, dimly lit offices of the Jet Propulsion Laboratory in Pasadena, California, someone is still listening. Listen carefully. There is not much time left.